In this section, we discuss how the free electron dispersion relation inside a crystal leads to the bands and band gaps that are so important in understanding electronic properties. We have discussed how free electrons can be described as traveling waves with a wave vector and a frequency. The energy of these electrons is proportional to the square of the wave vector, giving us a parabolic dispersion relation in the relationship between E versus momentum, or E versus K. As an equivalent basis, we can also use cosine and sine functions to describe these waves. Squaring either of these functions would indicate that the electron probability density oscillates with the wavelength of the wave function. Higher energy waves would indicate more frequent oscillation of electron density, while low energy waves would indicate a gradual change in electron density. In general, such free electrons would spend as much time near an atom as they would in between atoms. Although our free electron waves are periodic, the periodicity is not coherent with the periodicity of our atoms. Thus, for all of these wavelengths, the electron density is just as strong at an atom as it is between an atom on average. This makes the effective electron density uniform for all of these waves. Consider now wave functions that just happen to be coherent with the lattice of atoms in a crystal. This happens, for example, when the wave vector is pi over a. When the wave function is sine kx, there is zero intensity of the wave function at the atom location. All of the electrons are between the atoms. The cosine wave function, on the other hand, has all of its electrons at the atoms. Considering that the electrons are negatively charged and the atoms are positively charged, this leads to a significant electrostatic energy difference between the cosine wave function and the sine wave function. Thus, the energy of these wave functions depends not only on k squared, but also an additional potential energy depending on the phase of the wave function, whether the electrons start at the atom or the electrons start in between the atoms. The lower energy wave function will be the one that has its electrons at the atom, and the higher energy wave function will be the one that doesn't. Looking again at our dispersion relation of energy versus k, away from the critical k values, the dispersion relation E versus k is parabolic like that of a free electron. However, at k equals pi over a, there are discontinuities in the dispersion relation due to the wave function that strongly avoids the atoms and the wave function that's strongly attracted by the atoms. These two wave vectors have the same k vector, but different energies due to the difference in Coulombic potential energy. As we move higher in energy, we will continue along the parabolic dispersion relation until we reach another special k vector. When k equals 2 pi over a, the wave functions are again coherent with the lattice, but this time at twice the frequency. This interaction with the lattice sets up another gap in the dispersion relation at 2 pi over a and minus 2 pi over a. This effect will continue for integer multiples of 2 pi over a. It can be shown that the energies of the wave functions are continuous from k equals minus pi over a to k equals positive pi over a. We think of this as a continuous band of electronic states and call it an electron band for short. We call this region from k equals 0 to the first discontinuity the first Brillouin zone. Above the discontinuity, the energy of the electronic states is again continuous and make what we call a second electronic band. This region in K space is known as the second Brillouin zone. In our block diagram of electronic structures, each of these bands corresponds to a range of allowed energies for electrons. The gap in energy at the Brillouin zone edge corresponds to an energy gap in our block diagrams. The energy gap indicates there are no electronic states at any k vector, indicating that the energy is forbidden by the band structure. From this one-dimensional example, we expect many band gaps. However, in three-dimensional metals, this doesn't happen. In higher dimensions, we need to consider that the Brillouin zones are not isotropic. For a square lattice in 2 dimensions, the first Brillouin zone edge is at pi over a along the x direction and pi over a again along the y direction. The energy gaps that define the first Brillouin zone edge make a square in K space. The second Brillouin zone is just outside this square. For a wave vector along the 1, 1 direction, the wave doesn't reach the first Brillouin zone edge until it's at a vector significantly longer than pi over a. In a face-centered cubic crystal such as strontium, my E versus K relationship will give me a discontinuity at pi over a along the 100 direction. But instead, along the 111 direction, I don't see the discontinuity until a larger wave vector. This will give me a gap in the band at different energies depending on whether I'm looking along the 100 direction or the 111 direction. Because an electron can have a wave vector in any direction, I need to check all the different directions to know if I truly have an energy gap. In a metal like strontium, there is no energy gap because the bands along different directions overlap. Even though there may be an energy gap along one direction, there's another direction that allows a state with that energy. Semiconductors and insulators must then have a very different electronic structure that allows for an energy gap. In this case, there needs to be a significant energy gap along every direction where the bands don't overlap. For many properties we discussed, we're mostly interested in the electronic states at the Fermi level. This means that instead of worrying about all the bands in the various different directions, we can look only at the states at a particular energy. In our free electron model, the only states that exist at the lowest energy are at the origin. We call this the gamma point in the Brillouin zone in the very center. Just above the bottom of the band, all of the bands are parabolic and isotropic, such that they have the same energy in all different k directions. This means that the contour plot of constant energy is a circle in k space. All of these wave vectors on this circle have the exact same energy. In 3 dimensions, this circle is a surface in the shape of a sphere. The contour plot at the Fermi level is known as the Fermi surface. When the Fermi level is always within the first Brillouin zone, the Fermi surface is a sphere. When the Fermi energy is higher, such that the Fermi surface begins to touch the Brillouin zone edge, the gaps in the band structure start to distort the Fermi surface. When this happens, points and then holes form in the Fermi surface. The monovalent alkali metals have nearly spherical Fermi surfaces and behave like ideal free electron metals. The group 1b metals, such as copper, silver, and gold, have larger Fermi surfaces that just barely touch the Brillouin zone, and this distorts the Fermi surface away from a perfect sphere that can be seen in some transport properties. Multivalent metals, such as the group 2 metals and transition metals, have larger Fermi surfaces that extend into the second and even third Brillouin zone, making very complicated Fermi surfaces. A semiconductor or insulator has a wide band gap that separates the filled Brillouin zones from the unfilled Brillouin zones, such that it doesn't really have a Fermi surface, at least until it is doped.